Buenas noches. Buenas noches a todos. Bienvenidos a esta charla de eclipses lunares en astronomía india, que estará a cargo de una personalidad como la doctora Padmaya Venugopal de India. La doctora Padmaya tiene 26 años de experiencia de estar dando clases, haciendo muchas publicaciones también y escribiendo libros. Ella se graduó, tiene un PhD de la Universidad de Bangalore en matemáticas y astronomía y ha estado publicando muchos artículos, innumerables artículos en papers y en publicaciones de las universidades. Y también es autora de 2 libros. Un libro que se llama Eclipses in Indian Astronomy, que se publicó en 2009, y otro libro, que se llama Transits and Occultations in Indian Astronomy, que lo publicó en 2010. Y esta noche, como parte del ciclo de conferencias de astronomía en la India, ella nos va a platicar de la importancia de los eclipses lunares y posiblemente algo más. Así que para mí es un gran gusto, es un honor darle la palabra. Le voy a dar la palabra ahora, e invitarla a hablar. Esta charla va a ser en inglés, así que les doy la más cordial bienvenida también a todos ustedes, estimados personas interesadas en astronomía y alumnos de la universidad y de otras carreras. Bienvenidos todos y pongamos atención a lo que nos va a decir la doctora, muy amable. Welcome, Dr. Padmaya. Welcome to Galileo University.
Thank you,
it's an honor to have you here with us, and I'm glad to leave you the word to start your conferences.
Thank you, Professor. Shall I start now?
Yes, please. Go ahead.
So, a very good evening, good weekend to all my audiences from Galileo University, and I wish a very pleasant Sunday morning to all others who are from India and other countries. I, first of all, would like to thank Professor Edgar for giving me an opportunity to address the participants, and also I would like to thank the technical team, which has wonderfully designed my flyer and constantly helping me throughout. Professor, 1 second. Hello. ನಾನು ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ದೀನಪ್ಪ. So shall I start my presentation, Professor?
Yes, yes, Doctor. Please go ahead.
Yeah. So I had requested, in fact, Professor Edgar to include a verse, which he did it, and I'm really thankful for that. The verse goes as Chadayati Shashi Suryam Shashinam Mahati Cha Bhuchaya. This is a verse from Aryabhatiyam, and I'll go in detail about the meaning of the verse little later. Aryabhatiyam is a magnum opus authored by the great celebrated astronomer Aryabhatta, who belonged to 5th century. He is celebrated as father of Indian astronomy. In fact, he was the first to systematize the existing astronomical knowledge, and he was followed by luminaries of astronomers. And I again thank Professor Edgar for giving me this slide. I think this is in Spanish, welcoming all the participants. Now my talk would be based on eclipses. I'll not be confining myself to lunar eclipse. I'll be talking on both lunar and solar eclipse. There's not much a difference between the two. I'll not go into the technical details of it. However, my topic will be on inscriptional evidence of eclipses. So before I start the session, I wanted to give you a note on the scientific knowledge and scientific concept our Indian astronomers had before Aryabhatta, that is pre-Aryabhattan period, that is before 5th century, Indian astronomers knew the real scientific cause of eclipse. Now, the celestial play of sun and moon on eclipses caused sudden darkness, which excited the common man, and they were totally scared of sudden darkness. And there were so many myths prevailing for happening of eclipses, and people started believing that the eclipses happening or occurrence will be priorly indicated by omens like falling of meteors, etc. and so forth. But the real cause of scientific cause of the eclipses were known to the great stalwarts like Aryabhatta, Varahamihira. The verse which I was mentioning on the flyer is Chadayati Shashi Suryam Shashinam Mahati Cha Bhuchaya. This is a Sanskrit verse which appears in chapter 4 of Aryabhatyam, verse number 37. This translates as the moon covers the sun during the solar eclipse, and the great shadow of the earth covers the moon during the lunar eclipse. Also, we have a contemporary of Aryabhatta, that is Varahamihira, who also belonged to 5th century. He also explains the real cause of the eclipse, and he demolishes the myths that were entertained by the common public. He says the lunar eclipse, a moon enters the shadow of the earth, and during a solar eclipse, moon covers the sun's disk. As you all know, the actual cause of the eclipse, I'd like to brief upon the definition of solar and lunar eclipses. Most of you will be knowing it. However, I'll just brief it about. We all know that the sun and the moon, they take an elliptical orbit, and since sun moves along the orbit that is called the ecliptic, and moon moves along the elliptical orbit, which is referred to as moon's orbit, and the sun and the moon's orbit, they intersect at 2 points, namely ascending node and descending node. In Indian parlance, this is referred to as Rahu and Ketu. So every lunar month, we experience a full moon day and a new moon day. We all know that lunar eclipse happens on a full moon day and solar eclipse happens on a new moon day. We may wonder that why we don't experience a lunar and a solar eclipse on every full moon day and a new moon day. That is because of the different orbits or different paths the sun and the moon takes. And the moon should be close to one of its nodes. In case if it is a lunar eclipse, it should be a full moon day, that the sun and moon should lie on either side of the earth. In fact, their angular distance should be 180 degrees, and during a solar eclipse, sun and the moon should lie on the same side of the earth. That is, the longitudinal difference between the sun and the moon should be 0 degrees. And the moon should lie close to one of its nodes. Now, these nodes, ascending node and descending node, in Indian terminology are referred to as Rahu and Ketu. Now, this is the geometrical representation of a lunar eclipse. So, on a full moon day, sun and the moon are lying on either side of the earth. We find E represents the earth. We find sun and the moon lying on both the sides of the earth. The sun's rays falling on the earth will cast a shadow. And when the moon enters the shadow cone caused by the earth, we have the lunar eclipse. So here we have a mention of 2 regions, umbral and penumbral region. Normally in India, we consider only the umbral eclipse. So when the moon is partially into the umbral region, we have partial eclipse. And if it is completely inside the shadow cone, we have the total lunar eclipse. As a first example, I would like to take reference from Rig Veda. Rig Veda is an epic, sacred epic in our Indian system. And there was a mention of total solar eclipse, which happened in the year 3928 BC, that is around 4000 BC, at a place called Kurukshetra. The latitude and longitude of the Kurukshetra are mentioned here. Since the eclipse is solar, there was a new moon, that is, instant of new moon happened at 23 hours 36 minutes Indian Standard Time. And true sun and true moon, that is, true longitudes of the sun and moon are equal at that particular instant. Moon's latitude is very, very small. That is, moon is very close to one of its nodes. And Rahu, that is the name of the node. Rahu is the ascending node and Ketu is the descending node. In Indian parlance, we refer to as the nodes of the moon as Rahu and Ketu. In modern terminology, those two nodes are referred to as ascending and descending node. Now, this eclipse is referred to as Ketu Grasta Grahana. This is a Sanskrit version. Ketu Grasta Grahana means Ketu is the descending node. So moon is close to the descending node. And this eclipse is referred to as Ketu Grasta Grahana. So if the eclipse is total, we go to record 5 circumstances, namely beginning of the eclipse, beginning of totality, middle of the eclipse, end of totality, end of the eclipse. Now, we also go for calculating this half duration. Half duration we obtain by taking a difference of the middle of the eclipse and the beginning of the eclipse. That is called the first half duration. We have to note here that the first half duration will not be similar to the second half duration. The second half duration will be the difference between the middle of the eclipse and the end of the eclipse. So half duration is mentioned as 2 hours 53 minutes here. And also we go to calculate the magnitude of the eclipse. The magnitude is a ratio of the eclipsing body and the eclipsed body. Now, in case of the magnitude is greater than 1, then it turns out to be a total eclipse. In the case of lunar eclipse, we experience only 2 types of eclipses, namely total and partial. Whereas in the case of solar eclipse, we experience 3 types of eclipses: total eclipse, partial eclipse, and annular eclipse. Annular eclipse is a special case here. So when the solar eclipse is annular, the angular diameter of the moon will be little less than angular diameter of the sun. In the sense, if you can imagine 2 circles, one circle, that is 2 concentric circles. Now, if one concentric circle has a radius little less than the other one, then if you place one on the other, you can find one small line. Like the moon will be covering the sun, leaving one ring of light. So that is called annular eclipse. In Indian parlance, that is referred to as Valaya Grahana or Kankana Grahana. So in that case, the magnitude will be very close to 1 because the angular diameter of the moon will be slightly less than that of the sun. And this is the pictorial imagination of the artist, because we all know that the observation of the celestial phenomena was possible only after the invention of the telescope. And we all know that telescope was invented by Hans Lippershey. I don't know if my pronunciation is right. And it was first used by Galileo to observe the celestial bodies. So prior to that, the minute phenomena could not be observed by naked eye. So this is imaginary pictorial representation during the eclipse I'm talking about, that is mentioned in Rig Veda. Here we can observe that the sun and the moon are in the same line. Also, we have Jupiter in conjunction with the sun. Now, in case if you want to calculate eclipses which had happened so many years, centuries before, then we need to apply what is called delta T, that is a correction factor. The formula for this delta T is given by Stephenson and Morrison as -20 plus 32 u squared, where u is given here. So this delta T acts as a very important factor for the eclipses that are dated centuries back. So here, when we calculate delta T for the eclipse that is mentioned in Rig Veda, turns out to be 29.36 hours. That is 24 hours, we all know that contributes to one civil day. So plus 5 hours. So we have the eclipse, the solar eclipse that was observed on the day given, that is on July 26, 3928 BC at the place called Kurukshetra. Along with this solar eclipse, also one more phenomena was observed on that particular day, that is called Vyatipata in Indian parlance. That is nothing but the parallel aspect, which is referred as parallel aspect in astrology. That is, this phenomenon relates to the declination of the sun and the moon being identical. Here we can observe that declination of the sun and the declination of the moon are almost the same with a very small difference of 4 minutes. Also on that particular day, the summer solstice was experienced and the tropical sun was at 90 degrees on 27th July 3928 BC. Indian stand at 23 hours, 36 minutes, Indian Standard Time. So the next example I would like to take up is the Lord Buddha's Nirvana period. Lord Buddha, Nirvana period means the year of death of Lord Buddha. And during that year, there was a solar eclipse that was observed. The solar eclipse was observed on the year 559 BC, January 14th. Now, the solar eclipse, because it was a solar eclipse and it was observed as annular, the instants of sun and the moon, that is longitudes of the sun and the moon, are equal. And here I have mentioned it as NIR. That is Nirayana longitude of the sun and the moon. The Nirayana longitude means sidereal longitude. Now there are two ways of measuring the celestial longitudes of the sun and the moon. One system is referred to as sidereal system. Another one is tropical system. Earlier astronomers used the sidereal system to measure the longitudes of the sun, moon, and all the other heavenly bodies. So with reference to group of stars, the longitude and latitudes were measured. Now, in the current modern system, they go for what is called the moving origin. That is, first point of Aries is taken as a reference point, and that is referred to as the tropical system, which is the currently used system. So, Nirayana longitude, that is sidereal longitude of the sun and the moon, are almost the same, and moon is close to moon's latitude is very small. Moon's latitude is measured along the ecliptic, and that is a perpendicular distance of the moon from the ecliptic, and a moon should be very close to one of its nodes. So the angular difference between the sun's orbit and the moon's orbit turns out to be around 5 degrees. So if moon is less than, that is latitude of the moon, if it is less than 5 degrees, then the eclipse is sure to happen. In our text, that is eclipses in Indian astronomy, we have gone to discuss what is called the ecliptic limits. That is when the eclipse is sure to happen, and what is the limit wherein the eclipse is sure not to happen, and what is the otherwise case, whether it is possible or not possible. And this eclipse turns out to be annular, and hence we find that the magnitude is very close to 1. Now, I would like to take another example around 2451 BC, and this is a reference given by the erudite scholar, a Bengali astronomer who lived in the pre-independence era. He is Professor P.C. Sen Gupta, both a mathematician and an astronomer, and he has taken up examples on the phenomena, that is celestial phenomena, and mainly he has worked on eclipses. He has written a commentary on Brahmagupta's Khandakadyaka. Brahmagupta is a celebrated astronomer who was a successor of Aryabhatta, And Brahmagupta's contribution to mathematics and astronomy are enormous. I would not like to deviate from the actual flow of mine. So this reference is given by Professor P.C. Sengupta from Tandya Brahmana and Shatapatha Brahmana. These are Sanskrit scriptures, and the reference to eclipses, they help us to date the period of these scriptures. And this reference of the solar eclipse helps us to date the Sanskrit scripture actually. Now we again go for considering the longitudes of the sun, moon, etc. I don't get into the technical details of it. Here we have the circumstance of the eclipse recorded. Since this eclipse happens to be a total eclipse, we find that the magnitude is greater than 1. And now I would like to take up an interesting text which is called Grahanamala. The very name Grahanamala is a Sanskrit word which translates into garland of eclipses. This was authored by the petty king Hemangada Thakura when he was imprisoned. He lived during the rule of Mughal emperor. He was imprisoned, and during his tenure of imprisonment, he worked out a list of eclipses starting from Shalivana Shaka 1542 to 2630. Shalivana Shaka is a year, like a Jovian year, and it is supposed to have started from 78 AD. So if you want the current year or current era, we have to add 78. So 1542 plus 78 comes to 1620 AD or CE, current year, current era. And the end is up to 2630. He went on to calculate list of eclipses. So 2630 plus 78 gives us 2708 CE. Now he went on to calculate all the set of eclipses from 1620 to 2708. That is a very long period of 1089 years. And he went on to calculate 1432 eclipses in that period. And these eclipses are particularly visible in India. So in comparison to Appolzer, most of us are familiar with the astronomer Appolzer. He's an Austrian astronomer who lived in the period 1841 to 1886. And he has composed a catalogue of eclipses for over a long period, that is from 1200 BC to 2161 AD. And for this long period, he has listed around 8,000 solar eclipses and 5,200 lunar eclipses. But Appolzer had the advantage of knowledge of Copernicus and knowledge of Kepler. And it is really great of Hemangada Thakura, devoid of this modern knowledge, only with the available knowledge of computation of eclipses. He has gone on to list 1432 eclipses. And these eclipses, interestingly, are visible only in India. Eclipses which are visible in India, he has gone to list down. And this is a folio from his text. Just to have a feel of his text, I have gone for displaying these two folios. And you can observe that every verse closes with 2 lines. Now, I'll just go to tell you the contents of every verse. So in his listing of 1432 eclipses, the following are the details that are contained in every verse of his. So he says the year of the eclipse or year of happening of the eclipse. Then he mentions Duvrunda. Duvrunda means Ahargana. That is again an Indian word, which is nothing but the heap of the days or number of days since the beginning of that solar year. Then he mentions instant of full moon or new moon, as the case may be. If it is a lunar eclipse, he would have mentioned a full moon. And if it is a solar eclipse, that is a new moon. We have to understand it that way. Then he mentions about the nakshatra or asterism, starting from Ashwini, etc., from the eclipse day. Then he mentions about yoga. yoga is one of the concept we consider in Panchanga or ephemeris. So this is one of the parameters in ephemeris. Yoga by definition is the sum of the longitudes of the sun and the moon. Then he makes a mention of the weekday, that is number of days elapsed in the corresponding solar month. Then also he mentions the name of the lunar month and the half duration of the eclipse. Then beginning of the eclipse, which is referred to as Sparshakala in Indian terminology, end of the eclipse, which is referred to as Mokshakala in Indian terminology. And also he makes a mention of moon's latitude, whether it is to the south or to the north. So if the latitude is to the south, we have moon's latitude with a negative sign. Now, as a sample, we have gone on to take a list of eclipses, that is the date for which, that is the year of which he started calculating the eclipses, that is 1620. And also we have taken up two recent examples. Now the eclipse he had calculated the year 1620 was a total lunar eclipse, and we in Bangalore from India, we have under the under the guidance of Dr. Balchandra Rao, we have developed a procedure which we have named it as improved Siddhantic procedure, retaining the Indian framework and updating the parameters in the light of available modern formulae. We have gone for devising a new method of computation of eclipses, and also we have developed a software program. We have tested all these dates using our program, and we have compared the results with the modern ephemeris values, and we find very interestingly that the values differ only with a few minutes, and that is because of the other parameters like refraction, aberration, those concepts we have not taken into consideration. Maybe because of that, we have variation in minutes. Now, the first example I have taken here is lunar eclipse, which happened in the year 1620, June 15. That was on Monday. And we have gone for listing only full moon or new moon as the case may be, then beginning of the eclipse, end of the eclipse, and the magnitude of the eclipse. So first example is 1620. And because it turns out to be a lunar eclipse, it is obviously a full moon, which happened on 6 hours, 15 minutes Indian Standard Time. Then we have the beginning of the eclipse, then end of the eclipse, magnitude that is greater than 1, obviously states that it is a total eclipse. Then one more eclipse that happened after a difference of 6 months, 1620 December. That is again a total lunar eclipse with the full moon happening at 22 hours, 49 minutes. Then we have recorded the beginning timings, ending timings of the eclipse, and also the magnitude. Then in the year 1621, as a change, we have taken the example of a solar eclipse, which turned out to be annular. So annular solar eclipse happened on 1621, May 21st, Friday, and the rest of the details are listed down there. And we have 2009, April 14th, we had experienced a total solar eclipse. Normally this date, April 14th, why I have chosen is the solar calendar or the solar year commences on April 14th, and incidentally in the year 2009, April 14th, we experienced a total solar eclipse, and the new moon occurred at 8 hours 4 minutes, and the rest of the details we have listed. And the recent date we have taken is 2017, August 7, which happened to be a Monday. We had a partial solar eclipse, and the details are displayed. 2018, that is 4 years back, we have experienced a total lunar eclipse on 31st January 2018, happened to be a Wednesday. And now I have chosen this particular date, August 1, 2008. That is because I would like to give a small example from the epic Mahabharata. Now, most of you will be familiar with this Mahabharata. Ramayana and Mahabharata are two sacred epics of Indian system. And Mahabharata, it is mentioned that during the Mahabharata war, which took place in the place called Kurukshetra, which I had made a mention in the slide which I presented before. The Mahabharata war is supposed to have taken place in Kurukshetra, and during the Mahabharata war, between two syzygies means the new moon day followed by full moon day. So two consecutive syzygies, that is new moon followed by full moon. That is first new moon, there was a solar eclipse. Following full moon, there was a lunar eclipse, and the time interval between the solar and lunar eclipse mentioned in Mahabharata was 13 days. So normally the difference or the time gap between a full moon and a new moon, or a new moon and a full moon, will be normally 15 days. And during Mahabharata war, the difference between the syzygies was 13 days, and there was a mention that it is Aparvani. Parva means it is a gap of 15 days. Aparvani means less than 15 days. There were happening of eclipse. And so I got tempted to mention the recent happening. Now here, August 1st turned out to be a new moon, and we had experienced a solar eclipse. And 15 days later, there was a time gap of 15 days. 15 days later, during the full moon day, there was a partial lunar eclipse. So I'm tempted to quote this example here. This example, that is, this is a solar eclipse that occurred on August 1st, 2008. And the new moon, instant of new moon, was 15 hours, 42 minutes. Other details I would not like to go in detail. The other technical details we have here. Half duration, that's a very important parameter we require. And also we've gone for recording the circumstance of the eclipses. So in general for the world means eclipse begins at the time 13 hours, 33 minutes. According to this, the second column, these are the values which we have arrived at using our own software. Then we have compared the timings we have got with the modern ephemeris according to Indian Astronomical Ephemeris, which is published by Government of India based on the modern formulae and updations. So we observe that there is this very small difference of 1 minute. And the beginning of totality, according to our calculation, turned out to be 14 hours, 50 minutes, according to Indian Astronomical Ephemeris. This is as per the modern calculation, turns out to be 14 hours, 53 minutes. And middle of the eclipse is identical. Then end of the totality, we have a difference of 2 minutes. End of the eclipse, it is the same. As we all know, solar eclipse starts at some point. It moves along a belt, and the places having longitude and latitude along that belt will experience the solar eclipse, and it ends at another place. Then I'll just show you the figure, because this eclipse turns out to be a total one. The magnitude or pramanam in Indian parlance is greater than 1. So this is the eclipse which I spoke of, which happened in the year August 7, 2017. Now, the purpose of my choosing, the purpose of my choosing this eclipse is, this is one of the dates given by Hemangada Thakura, and this was observed in, I'm sorry, the date is not visible for me because of my screen. So this is the pictorial representation of the eclipse, a solar eclipse which happened on August 1, 2007. And this blue belt, that is a path of the solar eclipse. All the places which are located along that path would have experienced the solar eclipse. Beginning was at the beginning of that belt, and the end of the eclipse would happen at the end, that is last point of that belt. And also we find that there is a mention of Saros. The Saros means every eclipse will belong to what is called a Saros cycle. Saros cycle is a period of 18 years, 11 days, and 8 hours. The same type of eclipse will be experienced after a period of 18 years, 11 days, and 8 hours. And here we have now these are the photos that I've downloaded from NASA website. We have the other details like magnitude and altitude, gamma duration, etc. And now another example, that is after a gap of 15 days, we have the lunar eclipse happening. And this happened to be a partial lunar eclipse. I'll not get into the technical details of the calculation. Now we have the circumstances recorded. Since this lunar eclipse happens to be a partial one, we will record only 3 circumstances, namely beginning of the eclipse, middle of the eclipse, and end of the eclipse. Now this is a pictorial representation which I have gone for downloading from NASA website. And this is the eclipse I was mentioning. This is the date given by Hemangada Tapura. So as a sample, we just randomly picked a date and we went to verify. And this, of course, is an eclipse which we had experienced in India. That is a partial lunar eclipse that happened on August 7, 2017. Other details, we have gone for discussing all the other details. Since it is a partial eclipse, only 3 circumstances can be recorded. Now I have taken an example on February 3rd, 938. This is an example I have chosen from Epigraphia Carnatica. This example I have chosen because it was experienced in a place called Soraba from Karnataka. Myself being from Karnataka, Bangalore is the capital of Karnataka. So I thought I should discuss an example. And here we have a mention of Saras number. And I told you the duration of the Saras cycle. And since it is a solar eclipse, annular solar eclipse, we have the timings of the new moon recorded, true longitude of the sun and the moon. We find that they are identical, and also moon's latitude is very, very small. And we have the moon's node, that is Rahu in Indian parlance, recorded here. Annular eclipse, we have the ring of light appearing. So that is referred to as the annular eclipse. Again, this is a pictorial representation. Now the red belt tells us the path of the solar eclipse experience. So the places lying along that red colored belt, the people in that belt would have experienced this solar eclipse. And other details, because this is again a photo, that is imaginary photo I've downloaded from NASA website. Other details, this is from 5 million canon of solar eclipses. Espanak, he is referred to as Espanak and Muse. Espanak is referred to as eclipse guru. Guru means teacher in Indian parlance. Muse is a very wonderful astronomer who gives all the details at length. And we have also used Muse text, morsel of eclipses. And I have chosen one more date, that is 1148 April 20. The importance of this date is, this is an example I have taken from the book History of Sky on Stones, authored by Dr. B.S. Shailaja, who was the director of Jawaharlal Nehru Planetarium at Bangalore. She is a very active astronomer and astrophysicist, and she has authored many books. And this is one example I have taken from her textbook. And the importance of this is inscriptional evidence from Epigraphia Carnatic University. This eclipse is supposed to have happened on 1148 April 20. And the importance of this date, this was the date I have taken. And the inscriptional evidence is showing only the solar eclipse. Interestingly, we could go for finding many more phenomena which are of importance. Now, this is a total solar eclipse. And the summary, as we all know, we have to go for recording 5 instances. And we found that on the very same day, that is 1148 April 20, we found that the sidereal longitude of the moon. Sidereal longitude means the longitude measured with the reference as fixed group of stars. So we have the sidereal longitude of moon and the sidereal longitude of the Mercury. Mercury was in retrograde motion. So we found that very interestingly, these two longitudes very close to each other. So we checked for lunar occultation, and we had experienced a lunar occultation. That is, mathematically calculating, we learned that there was a lunar occultation also, which was not mentioned in that inscription. Also, we had one more phenomena happened on that very same day, that is Vyatipata, which I had mentioned long back in the beginning of my talk. Vyatipata is a phenomena wherein the declinations of the sun and the moon are identical. In modern astronomy, normally the heavenly bodies are located using the coordinate system, right ascension and declination. So we found that during 9 hours on the very same day, the declination of the sun and the moon almost were the same. So Vyatipata is nothing but the parallel aspect that is referred to in astrology. Normally, Vyatipata is of not much of relevance to astronomical concepts or computations. And one more interesting phenomena we had observed. These are the observations made by us based on the longitude of Mercury. So Mercury transit, most of us have heard of this transit, and many of us have also witnessed the Venus transit in the year 2012 on June 5th. And many planetariums across the globe had arranged for the observation of this transit. So this transit is a very interesting phenomena, which is very much similar to that of the solar eclipse. So in solar eclipse, we find that the participating bodies are sun, moon, and we from the earth are the observers. Whereas in Mercury transit, participating bodies will be Mercury and the sun. And interestingly, during the transit, both Mercury and Venus will be in the retrograde motion. And this transit phenomena is a unique concept that is applicable only to Mercury and Venus, because these are the two planets which are inside the orbit of the Earth. So during the Venus transit, the Venus transit which we had witnessed in the year 2012 is a special transit because that is the last transit of the century, and the next transit, Venus transit, will be witnessed only after 105.5 years. This is a pair spaced 8 years, 105.5 years. So the Venus transit, which happened earlier to 2012, was 8 years back, that is in 2004. So after this 2012 transit, the next Venus transit would be experienced only by our next generation. That is after 1 century, after 105.5 years. That is, the next century is expected to be observed in the year December 2117. And 8 years later to that, December 2125, probably our 3 or 4 generations later, they might be experiencing the next transit. And this is another important, interesting phenomena which we had observed. Now here again, during the transit, we have to have the longitude of the sun and Mercury identical, and Mercury's latitude. So Mercury's orbit, we will be intersecting the sun's orbit, which is referred to as ecliptic at 2 points. So the 2 intersecting points are referred to as node. These are the nodes of Mercury. So when Mercury is close to one of its nodes. Now this mention of south refers to Mercury has -8 latitude, and the other details are displayed here. So transit also has 5 circumstances recorded. It is similar to a total solar eclipse. We have beginning of external ingress, we call it as ingress here, then beginning of internal ingress, then middle of the transit, end of internal egress is moving out of. Now, if we observe the transit, most of us would have experienced it. The Mercury or Venus covering the sun. Sun is very big and the diameter of the sun is not at all comparable with that of the angular diameter of Mercury or Venus. So Mercury or Venus moves like a black spot on the sun's disk. And we have one more example considered, that is annular solar eclipse on 11:30 October 4. This is an example I have chosen from Epigraphia, Carnatic University. And this example is from, this is an inscriptional evidence from Ramalingeshwara temple in Ballari Taluk. Ballari is again a place in Karnataka. So I'm tempted to quote this example also. This is an annular solar eclipse and the summary is here. Magnitude will be slightly very close to 1. Okay, because we have the magnitude as a ratio of the eclipsing body and the eclipsed body. So the ratio of the biggest sun's angular diameter will be slightly more than that of the moon's angular diameter. It will be like 2 coins. One coin, that is, we have 5 rupee coin and 1 rupee coin. If you can imagine, in India, I can say that Indians can imagine that. I don't know about the size of the currencies at Galileo University. And this
similar.
Okay, sir.
Okay, yes, similar.
Okay. So this is the example, that is pictorial representation of the eclipse. As I had mentioned, because there were no telescopes, and the eclipses would be viewed through naked eye. And here we have the imaginary figure by an artist based on the inputs given by the astronomers. The red belt shows the passage or the path of the solar eclipse, annular solar eclipse. And we have another interesting date, that is 978. And this is again an example from Karnataka. So I, being a person hailing from Karnataka, I'm tempted to quote more inscriptional evidences from Karnataka only. This is an example of an annular solar eclipse which happened on 8th June 978 AD. And annular solar eclipse implies that the magnitude, that is the ratio of the eclipsing body and the eclipsed body, is very close to 1. And this is a very interesting example which I would like to quote. This is a lunar eclipse on 8th November 542 AD. This very same date was discussed by my friend Dr. Rupa in her previous talk. This is the date I have chosen from the magnum opus Abhignana Shakuntalam. Kalidasa is the author of the magnum opus. He is a poet and also partially an astronomer, I would like to quote, because he gives an example of an eclipse, a lunar eclipse, which happened on 8th of November 542 AD. And we have all the circumstances recorded here. Now, this eclipse turns out to be a total eclipse. Also, this eclipse belongs to Saros number 83. Immediately after the eclipse, the moon goes to have a conjunction with the star Rohini, that is Aldebaran in modern parlance. So we have this verse from Abhignana Shakuntalam, belongs to chapter 7, shloka, that is verse number 22. Now, I'll not go to read the Sanskrit verse. I'll read out the English translation of it. So the author says, that is Kalidasa says, "O dear Shakuntala, you are standing before me, who am now rid of the illusion of forgetfulness. O lady with a beautiful face, at the end of the lunar eclipse, Rohini approaches to conjoin with the moon." So the author gives a simile of Shakuntala joining Dushyanta to this Rohini conjoining with the moon. So this is a very interesting and wonderful example, astronomical example he gives. So this astronomical references helps us to date the books or the period of the occasions which we consider. Now, this is the calculation or the details of lunar conjunction. Now, lunar conjunction need not have to be an occultation. So conjunction, if it has to become an occultation, conjunction means the moon's longitude and the star's longitude are the same. So the occultation, if it has to happen, then you should have the condition as it is prevailing in the case of eclipse. That is, moon should be close to one of its node. Only then occultation happens. It is like every full moon day and new moon day, we have the sun. Full moon day, sun and moon will be lying on either side of the earth with a longitudinal difference 180. And on new moon day, the sun and the moon will lie on the same side of the earth with the same longitude. But that doesn't mean that we will have a lunar and a solar eclipse. For lunar and a solar eclipse to happen, moon should be close to one of its nodes. So occultation is also a phenomena similar to that of the solar eclipse. So this is a very interesting example of a solar eclipse which happened in the year 1504 March 16. I'm sorry, because a part of my screen is not visible, so I'll have to look into the reference for that date. So this is a solar eclipse which happened in the year 1504 March 16, and that was on a Saturday. I'll just show you the pictorial representation of it. Now, this reference I have taken from the erudite scholar R.C. Kapoor, who is an astronomer and also an astrophysicist. He has given this reference in one of his research papers, and this is a pictorial representation of a team of a Sikh religious group, SIKH, Sikh religious group, which is led by the Guru, that is Guru Nanak, on his entourage, on his tour to Kurukshetra. He and his team witnessed a solar eclipse on that particular day, and that is the date I had taken up. So this turns out to be a solar eclipse, which is partial. So only 3 circumstances would be recorded here. And I have taken up an example of Bhaskara II. Now the Bhaskara II very name indicates that there was also Bhaskara I, who was there very much. He was one among the astronomers in the lineage of very popular and dynamic and contributing astronomers. Now, Aryabhatta I had mentioned to you in the beginning. Aryabhatta was referred to as father of Indian astronomy. He had authored Aryabhatiyam, which is a very popular and an important text. I can as well call it as a Bible of Indian astronomy. So Aryabhatta could be understood only because of commentary by Bhaskara I, because Aryabhatta's style is cryptic and aphoristic, and common man could not understand what the contents of the text are. The text could be understood because of Bhaskara I's commentary. Bhaskara I also was a very celebrated astronomer who had made the common lot or the astronomers to understand what Aryabhatta's contents are, what Aryabhatta's model is. Also, he has given a very interesting example, that is very interesting formula for sign approximation. So most of us, I hope, are mathematicians as our audience. So if we are performing an experiment that is in physics lab, that is simple pendulum experiment, most of us, when we were in second PUC or so, we would have experienced that. So our teacher would have asked to move the pendulum to a very small angle. And how small the angle should be, teacher would have directed us. So when the angle theta is very small, we will go for approximating theta to 1. And that is, theta will be approximated to 1 if it is very small. And sine theta is approximated to theta. Now, the sine approximation formula given by Bhaskara I gives us, I don't have that slide, gives us the values which are as large as 90 degrees. So, using the calculator, if you go to calculate the values of theta, that is theta ranging from 0 to 90 degrees, whatever interval you want to take. I had taken the interval as 10 degrees. So, 0 to 90 degrees. Now, if you go for listing the values of sine 0, sine 30, I'm just talking about the standard angles, sine 30, sine 45, etc. Also using the calculator, if you go for calculating sine 15, sine 45, sine 30, sine, etc. and so forth, using Bhaskaravan's sine approximation formula, if you go for calculating, the values are very, very close. Why I'm telling you this is, this sine approximation formula has inspired the Maharashtrian astronomer Ganesha Daivagnya to devise a model, that is a computational model which is devoid of, which is completely dispersed with the trigonometric ratios. Trigonometric ratios are replaced by beautiful numerical approximations. These numerical approximations are possible by Bhaskara-1's sine approximation formula. So coming to Bhaskara 2, he belonged to 12th century, and in India we had recently celebrated 900 years of Bhaskara in the year 2014, and many places the conferences, seminars were arranged based on Bhaskara's contribution. He again is one of another celebrated astronomer who had given one important correction to moon, which is called variation. Moon, because it is an erratically moving body, which is moving at the rate of 13 degrees per day, we need to go for adding minimum of 100 corrections to moon as per the modern astronomy. But earlier days, only important corrections were considered for moon: evection variation, equation of center, and moon's equation. So these are the 4 important corrections that were considered earlier, and Bhaskara is one of the contributors of one important correction. Also, he has made mathematics a very lovable, enjoyable subject by commoners by his poetic way of presenting the statement problems. He has authored a very popular text called Leelavati, in which he goes to give the statement problems which could be enjoyed, understood, and calculated by common public. And we had taken examples from Bhaskara's period. He belonged to 12th century. So as an example, first example, I had taken 1620 December 9. Now I've not gone to give many details here. I've just stated whether it is a total or a partial eclipse, whether it is a lunar or a solar eclipse. So December 9, 1620 happened to be a total lunar eclipse. And also I mentioned the half duration of the eclipse. Then the remaining 3 examples are more or less in the period of Bhaskara II. So these are some of the examples I've taken. And I think I would like to conclude my talk, Professor. Shall I?
Thank you very much. Thank you. Thank you so much for your interesting and beautiful talk. We have some questions for you.
Yes, Professor.
You mentioned yoga. I think yoga as the sum of the longitudes of the sun and the moon. Is that
exactly.
right?
Exactly, Professor.
So this is can you elaborate a little more on the yoga aspect?
Yoga aspect, that's a parallel aspect in astrology normally they use. It has no much relevance in astronomy, Professor. There are 2 important yogas, Vyatipata and Vaidriti. So Vyatipata, the longitude, the declinations of the sun and the moon will be equal. And Vaidriti, that is another yoga. That is, some of the longitudes are 180 and some of the longitude with 360. That has relevance. The other yoga, there are totally 27 yogas mentioned. Only the Indian names, I'm not very much familiar with it. Indian names are listed there. So that is a part of Indian astronomical, that is part of Panchanga. That is, Panchanga is an almanac which is used among the traditionalists in India. And different matas. Matas means religious practicing bodies. They will adhere to one particular Panchanga or almanac, and the religious group which follows that particular mata, they will follow that Panchanga.
Wow, that's way Wonderful.
Thank you.
Amazing. We have another question here. You mentioned the Saros cycle.
Yes,
Saros cycle, right?
Yeah.
Our question is, what is the difference between the Saros cycle and the Metonic cycle? Metonic cycle.
Yes. Metonic cycle is similar to the Saros cycle only. It is a period of 19 years. Metonic cycle, same type of full moon and new moon will be repeated. That is time. Full moon and new moon we have every lunar month. So after a period of 19 years, same type of full moon and new moon will be repeated. That is Metonic cycle.
Okay, thank you. Thank you very much. And the last question is about Bhaskara periods, 1 and 2nd. In what period did he develop his computational model?
12th century.
12th century.
Yes, Professor. 12th century.
And then this was his first period or his second period?
This is Bhaskara the second, who belonged to 12th century. Bhaskara first, he was a contemporary. He was a commentator of Aryabhatiyam. He belonged to 6th century, Bhaskara 1. This is the second Bhaskara who belonged to 12th century. There are two Bhaskaras.
Two Bhaskaras, yes.
Yes, Professor. In Indian astronomical lineage, two Bhaskaras are there. Both are great contributors to the field of astronomy. Bhaskara 1 had come up with sign approximation formula. Bhaskara 2 gave the correction factor for moon.
The correction for the full moon.
Yeah, not full moon. The that is longitude, to find the longitude of the moon, because moon is erratically moving body. Many correction factors are to be incorporated, and the main important correction factor that was considered both in India and the other part of the world, they were considering equation of center.
Why are these corrections needed for the moon? Sorry to answer.
That's okay. Equation of center is because normally while calculating, it is a common concept. Even in modern astronomy, we assume that moon is moving in the circular orbit. But thanks to Kepler, today we know that all the heavenly bodies move in an elliptical orbit. So because of the conversion from circular orbit to elliptical orbit, we need to incorporate a correction which we call it as equation of center. Even in modern astronomy, also we do that. And there are other corrections, because moon is comparatively a smaller body. It will be perturbed by the gravitational pull of the other bodies. So we need to go for applying the other corrections. But only 4 important corrections were applied earlier. Evection, variation, annular equation, and equation of center.
Wonderful. We have learned a lot in your talk, and I think this will be a very important document, because it's going to be recorded for our future study with the students which are studying lunar and solar eclipses. And because it is invaluable, because the richness of the cultural and the dates, the date you mentioned, 8 November in 542 CE. Right?
Yeah. Wow. That is Kalidasa's example.
Kalidasa's.
Yes, Professor.
Wow. So we are amazed. We need to understand more about the Indian culture also.
Thank you, Professor.
So we are very thankful with you. Thank you for your time and for sharing all this valuable knowledge with us. We are very, very excited and thankful with you. Thank you very much.
Thank you, Professor. Thank you for your opportunity, for providing an opportunity for me to share whatever little I knew. And we would hope to go for a collaboration in the days to come. I'm really thankful to you again for giving me an opportunity. Also, all my team members, we are all grateful to you. And we are all grateful to our teacher, our mentor, Dr. Balchandra Rao, for training us.
Yes, Dr. Balchandra. Our greetings to Dr. Balchandra Rao. With this, we are closing. Oh, we have another, in next month, we have another talk about astronomical tables.
Yes, Professor. My colleague, Dr. Uma is making the presentation.
Right. Wow. So it has been a wonderful cycle of talks. Wonderful. We have learned many things. So it's not only about astronomy and mathematics, but about culture and history. So very, very valuable. Thank you very much for your time. And we are going to be in touch, looking forward for more lectures in the future.
Thank you. Thank you, Professor.
Thank you so much. And I'm going to say goodbye to our audience in Spanish, if you allow me.
Yeah, Professor. Definitely.
Okay. Bueno, muchas gracias a todos. Con esto terminamos esta conferencia del ciclo de conferencias que estamos llevando a cabo con astrónomos de India. Y ha sido muy valiosa, tanto en el aspecto cultural como astronómico y matemático. Los esperamos en las próximas conferencias. Que pasen buena noche y que estén muy bien. Good morning, good evening, and we'll be in touch, Doctor Padmaja Benugopal.
Yeah, thank you.
Thank you.
Thank you, Professor.
Estamos ya.